Let's review availability. Now, with availability, there are probably a couple of different schools of thought on it. One is that where you have a single system, possibly a small system, possibly an embedded system, and you want it to be particularly reliable. So you think in terms of, say, a mobile phone or a small control system. You probably want that to be quite reliable. The other circumstances where you have a large system, like a web e-commerce site or some other web system, certainly you have it'll be a server-based system or a cloud-based system or something of that nature. Now, the approach to availability in each of those circumstances is quite different. Now, I'd like, let me deal with the embedded system first. With those systems, reliability or availability seems to be mostly a matter of programming. That is, the program should not have faults and should prevent faults in some fashion. It's not largely a matter of architecture, but having said that, to some extent it is. But to a large extent, it's a matter of programming. Now, here I'll deal with the cases where it is a matter of architecture. So we're dealing with circumstances where we do have possibly a number of processes and process instances that we can deal with. Now, there are some situations that do have quite enough problems without dealing with unreliable systems. All right? So air traffic control, for example, they've got enough problems to worry about. The last thing they need is unreliable systems. Now, in these circumstances, we can take some lessons from Erlang. Now, Erlang is a language. It was developed and used to build telecommunication systems for a telecommunication company in Sweden. Now, those telecommunication systems initially were written in C and then C++. They had what was termed a high failure rate, and a high failure rate, they pointed out in these circumstances, is something like 2 seconds downtime a year. And you might think that's brilliantly reliable, but in a telecommunication system it was not considered to be particularly reliable. So the Erlang language was used to develop a system. Now, aside from the language peculiarities that led to a fairly simple system, there were some architectural features they had there as well. And the major one was they built a system with a lot of small processes, a lot of small concurrent processes. And these concurrent processes could communicate to each other, but there was no common memory. There was no swap over at all. Right? Largely, they let the processes fail. If a process went faulty, it crashed. They let it crash, and then they recovered. Right? They didn't try to prevent the failures. It just, if it was going to fail, it failed. So largely, they achieved a super reliable system based on possibly faulty components. Now, this is something that we can use architecturally. So we've achieved, we can structure a system so that we assume that the components of the system may be faulty and work off that. So if they're faulty, they can fail. We just simply let them fail and we restart and start from a known state and recover. And we can do that fast enough that this becomes transparent to, or sorry, not transparent, but hidden from the end users. Tactics for achieving availability. Classically, we try to prevent failure by, say, filtering data or validating outcomes. So we detect potential causes of failure beyond bad code. Our code is good, all right? So all that's left is the incoming data. We can detect a failure. Now, this is assuming we have independent processes, and we have some form of monitor about the place. Now, we can detect by either a process puts out a heartbeat and we watch for that heartbeat, or we can from time to time ping each process and see if there's a response. And if there's not a response, we deduce that it's gone bad and we just kill it. Or we can catch an exception, so that the process could throw an exception and we can catch those. Right. So that's preventing failure and detecting failure. We can cope with failure. Now here we have faulty components, okay? And it's gone faulty. We have a system that can cope with failure. We can allow that one to go faulty. Either we have a dual process and we simply fail over to the other process and just flush the faulty one out and restart it and bring it back up again. Same with the process. If it's gone faulty, we kill it, flush it out, restart the process, and go on from there. We obviously have to put into place the transactions, or some concept of transactions, so that we can either redo or recover or roll back the transaction that we were in the middle of doing. And that's sometimes a matter of architecture, sometimes a matter of programming. Recovering from failure, restart in a known state and then recover from there. This is as opposed to trying to repair something that's there in the memory. Now, a measure of reliability, I was speaking to a product manager, I think he was, from Avaya, who's a telecommunications company, and they put out software for mobile phones. Now, he pointed out that the phones cost very little in comparative terms, or compared to computers, I suppose. The cost of recalling a phone to fix a bug would be exorbitant. It would exceed the cost, the profit made from the phones by a large margin. So to him, a recall was just not a possibility. You just could not have a bug in that system that you released that would cause a recall. So they treated reliability or availability very seriously. They did their testing very seriously. Reliability, which is an aspect of availability, often depends on the criticality of the thing. So how much effort you put into reliability depends on how critical the reliability is. Now we have some measures there. If a failure would be merely an inconvenience, then you probably wouldn't worry about it. But if it's going to cause a loss of income, you might worry a bit more. If it's going to cause a loss of life, then it's probably pretty serious and you probably should pay attention to it. But different systems have a different concept of reliability. A financial system, for example, my understanding is that a financial system can crash, but it dare not lose any data. That's money, and you dare not lose it. So you can fail, but don't lose the money. Telecommunication system, that as far as in my experience, they can actually crash and they can lose the data, but they've got to recover. Now this is because the telecommunication software we're dealing with is the stuff that's downloaded into switchboards and left there to run for a couple of years. So the software on the particular module on the switchboard could get a problem. Now it can just simply flush out the data and restart. Okay, now the data may be lost, alright, the messaging system itself has this concept of, well, individual messages may fail, we'll just send the message again. So the telecommunication system has to repair itself and keep going. A control system used to run a factory, particularly a factory where there is potential danger about the place, the whole idea of reliability there is that whatever else it does, it should not lose control. That it must, if all else, if it's going to fail, it should fail in a graceful degradation, so that it brings the whole thing to a safe halt. And I have seen, I think it was a couple of 100 tons of white hot metal coming down the rollers to be rolled. When that's happening, you really don't want the whole control system to go pear-shaped. Now, achieving availability, as I've spoken before, you have an architecture where you assume that the various modules may fail, and you put things in place so that the modules can fail, recover, reset, and get back so that it works well. You have frequent integrity checks, so it's fine to think that each module might have the brains to detect it's going bad and kill itself, but that's not necessarily true. So you may have to have some monitoring system that monitors a process and determines that that process has gone bad and to kill it and flush it out. So in those circumstances, you need to provide a graceful degradation, not a total collapse.